Hi, good morning. Today we have another question on nodal analysis. The question read, using nodal analysis, using the concept of supernode, find the current I in the figure. So this is the current I, and we are asked to find the value of this current. So we are going to employ nodal analysis. If you check very well, we have a current source in milliamps, voltage source, and a voltage source, and another voltage source. Then we have our resistors given in kilo ohms, kilo ohms, kilo ohms, and kilo ohms. So we employ nodal analysis in finding the value of this current. So that's what is required of us. And if you know from what we know that for us to use nodal analysis, we would have to give nodal voltage around the circuit. So we first of all consider our reference point or our reference voltage or reference node. So reference node is usually like the node where much elements are connected to. So you can see that this very node carries that have that property. It has a voltage source, a resistor, and a voltage source connected to it. So this node altogether gives you the reference node. So let me just put that out here. I would have this to be our reference node. And remember, your reference node is at 0 volts, right? So we are done with the reference node. I'll take it one step at a time, and then let's label this node here V1, right? Let's label here V1. And if we label that place V1, then we simply have that the voltage at the positive side of this voltage source 20 volts, or just say 20, is equal to the voltage as the positive side of that voltage source, which is 0, minus the voltage as the negative side, which is V1, right? Because if this node is V1, that means this node is also V1, so that's equal to V1. So from here, we can conveniently get that V1 is equal to minus 20 volts, right? So the value of V1 is equal to minus 20 volts from this first. So we have node V1 here. So the second node we want to choose is, let's from here we have another node. Let's call this V2, right? And let's call this node V3, right? So if we call that if we call this node V2, and we call this node V2, and then we call the other one V3, then let's see what is obtainable. We see that this voltage source, this given voltage source here, has 15 volts, is equal to the voltage at the positive node minus the voltage at the negative node. What's the voltage at the positive node? V2. That's V2 minus the voltage at the negative node. You see that this is the negative side, this is the positive side, so that's what I'm making reference to. So that's V3, right? So from here we'll write what we want to do now is we want to write V3 in terms of V2. Sorry, V2 in terms of V3. So we'll make V2 subject formula. You get V2 to be equal to V3 plus, that's take V2, take this V3 to the other side, that would be V3 plus 15 volts, right? So that would be equal to V2, the nodal voltage V2 is equal to V3 plus 15 volts. This might be your equation 2. So the next in our agenda, we know that the voltage at this side is 0 volts. Here is 0. Here is also 0 volt because they are all connected. There is no circuit element between here up to this. Is just a connecting wire. So this is going to be 0 volts, 0 volts here. So we have 0 volts here, and then we'll give this node, this very node, let's call it, we've used V3, so let's call it V4, right? So in that case, we know that our 30 volts is equal to the voltage at the positive side, which is V4, minus the voltage at the negative side, which is 0. That's voltage here minus voltage here. You can trace 0 back to this place. So you can't say this is V3 because there's a resistor here. So you can't there has to be a voltage drop or difference between that resistor. So the same voltage drop can apply here, or node voltage V3 can't apply here. So we have this to be, from here we have our V4 to be equal to 30 volts. So the manner at which you label this thing is just up to you. Then we can see that from here almost all the voltage are known. V1 is known, V4 is known, but we don't know V3 yet, but once you know V3, we automatically would know V2. Is that taken? So if that's taken, we'll delve into applying nodal analysis. And you apply nodal analysis at nodes where you don't know the values of the voltage. So here we know the value of V1, so there's no need of applying nodal analysis here. We also know the value of V4, so there's no need of applying nodal analysis here. So it's only this node V3 that we don't know the voltage value of the voltage V3 that will apply nodal analysis. So by nodal analysis, nodal at node V3, at this node, we apply nodal analysis and see what is obtainable. So by doing that, we employ the concept of supernode. So what supernode simply means is this, for instance, they consider to be a kind of simple node, right? So this is considered to be a kind of simple node because it contains this voltage source. So we want to take out that voltage because we can't actually write KVL equation through voltage source, so we have to take that out. So this is the node we'll be considering. And remember, this whole of this node is what? Node V3, right? So current to enter from here, current to enter from here, and even from here, or leave as the case may be. So we know that at node V3, we have the current leaving, because this node is V3, that means here too is also V3. By inspection, you know that they are at the same potential, since no element is connected between these two sides, so they are the same potential. So we have current leaving through this, current leaving through this, current leaving through this, and current leaving through here, and leaving that for this node alone. So for node V3, first of all, take current leaving through this, right? So let me quickly label this. If current is leaving like this, here has to be the positive terminal, here has to be the negative terminal. If current flows like this, remember from our last discussion, we said current leaves through, it enters the resistor through the positive terminal and leaves through the negative terminal. So if current leaves through this, remember this is the direction of current we want to specify. If current leaves through here, we would have current leave through here, then you have a positive voltage drop here and the negative voltage drop here. The same thing for this very one. Since we are writing the KCL equation for this resistor, not the supernode, because we've taken out the voltage source, we're only considering here. So current is leaving, current is going down. So here is going to be positive, here is going to be negative, right? That's for this 1K resistor. Then for the 3K resistor, we have also that current is leaving. So the thing is, you can actually specify which direction of current you want, whether leaving or entering. Whichever direction you specify, it doesn't matter. You can decide to choose your own current to be entering. So whichever one is still the same. So if current leaves or current flows down, then we have here to be positive, here to be negative. So this we've labeled all the sides. So now, what is the value of this current leaving? Remember, we said if current is leaving, we'll give it a negative sign, right? So that's minus. What's the value of the current leaving? Is the voltage at the positive side minus voltage at the negative side divided by the resistance. So what's the voltage at the positive side? That would be V3. So that would be V3 minus what's the voltage at the negative side of this 2K resistor? That's V4. That's V4 divided by 2K resistor. Now, you don't need to convert the resistor to ohms, or because if you leave a resistor in kilo ohm and currents in milliamps, they all work together and are compatible very well. So we are done with this branch. The next is this branch. The current is leaving, so it's still minus. So what's the value of the current leaving? That will be voltage at the positive minus voltage at the negative divided by the resistance. Voltage at the positive side, remember, is still at node V3, so that will be V3 minus voltage at the negative side, which is here. You can trace it down to ground. That's 0 divided by that resistance is 4 kilo ohm. Then the next is this current leaving, this very current here, and that would be equal to voltage at the positive side, which is minus. Because since it's leaving, we'll give it a negative sign. Voltage at the positive side is equal to V2 minus voltage at the negative side is ground, which is 0, divided by your resistance, which is 1, right? Then we'll turn our attention to this side, so that will be minus because the current is leaving this node. So since it's leaving, you have minus. What's the voltage? What's the current passing through this 3K resistor? That's the voltage at the positive side here, which you can trace back to node V3. That will be V3 minus what's the voltage at the negative side? V1 divided by the resistance, which is 3, right? So I'm done with this. Then how about this? The value of this current is just 10 milliamps. Since it's leaving, we'll say minus 10 milliamp, and everything is equal to 0. Remember, this is a statement of Kirchhoff's current law. So everything here we've just done is from the circuit. The next is just to apply our algebra to solve for the unknown. So substitute, we have minus V3 is unknown, minus V4. Remember, our V4 from here is 30. That minus 30 divided by 2, minus V3 minus 0 is just V3 over 4, right? Then minus V2 minus 0. Now remember V2 here we said is equal to V3 plus 15. So that will be V3 plus 15 here divided by 1, right? Because V2 minus 0 is the same thing as V2, and that V2 is equal to V3 minus 15. So that will be divided by 1 minus V3 minus V1. That would be V3 is unknown minus V1. V1 we said is equal to minus 20, so that's minus 20, all divided by 3 minus 10 is equal to 0. So quickly we rush through this. That's V3. So okay, before we rush through that, we'll multiply all through by the LCM of the denominator terms. The LCM of 2, 4, 1, and 3 is 12. So if you multiply all through, that will be minus 12 into V3 minus 30 divided by 2 minus V3 over 4 times 12 minus V3 plus 15 over 1 times 12 minus V3 plus 20 over 3 times 12 minus 10 times 12, right, equals to 0. So we have that minus 12 divided by 2, that's minus 6 into V3 minus 30 minus 12 divided by 4 minus 3 V3 minus here 12 times V3, you have 12 V3 minus 15 times 12, that will be minus 15 times 12, that will be 180, and minus 12 times V3, 12 divided by 3, that's 4 times V3, you have minus 4 V3, then plus 12 divided by 3, that's 4 times 20, you have 80, minus 10 times 12, you have 120 is equal to 0. So from here you open the bracket further, minus 6v3 minus 180 minus 3v3 minus 12v3 minus 180 minus 4v3 plus 80 minus 120 equals 0, right? So from here we'll go further, simplify further. Minus 6v3 minus 12v3 minus 4v3, you add everything, and then minus 3v3. If you add this, and this, you get minus 25v3, right? Then minus 180 minus 180 plus 80, that will give you minus 280. Minus 280 minus 120, this should be minus, this should be plus, this should be positive 180, because we have minus 6 times minus 30, that's plus positive 180. So this and this plus 180 minus 180 cancel out, that gives us 0. Then plus 80 minus 120. All right, pardon on my some of my mistakes. I think I made a mistake at the beginning part here. If 15 is equal to V2 minus V3, then if you make V2 subject formula, it's going to be V3 minus 15, right? This is minus. So from here, where we substituted V2 should have been V3 minus 15. Here should be minus 15. And if you open this bracket, you'd get plus 180, right? Because 15 times plus minus 12 times minus 15 will give you this. Then similarly, I made a mistake here. So if you open these brackets, the minus should affect both of them. So here should carry a minus, and here should carry a minus. So these are the little mistakes I made. So I'm sorry for that. So please, if you add everything together, if you add this, and this together, you get minus 25 V3. Then if you add this and this is plus 180 from here. So if you add 180 plus 180, that will give you 360. Minus 80 minus 120 will give you minus 200. And 360 minus 1 and 200 will give you plus 160. everything becomes 0. So if you make V3 subject formula, that will give you 160 or minus 160 divided by minus 25, which is equal to 6.4 volts. So you get your V3 to be equal to 6.4 volts. So in the process of the question, the main part of the question asks us to look for I, right? Find this I. So to find I, will apply Kirchhoff's current law to this loop. So to this node. Applying Kirchhoff's current law to that node, I will talk of this current entering, this other one entering from here, and this one. So if you apply Kirchhoff's current law by KCL at the ground node, we have if you apply KCL at the ground node, this current is entering, that's positive, that will be I. Then the other current from this place is also entering, so that will be positive as well. So this is going to be positive. And what's the value of this current that is entering that is positive is going to be V3 minus 0 over 4. So that will be V3 minus 0 divided by 4. And how about this other current that is entering through here? So that will be V3 minus V4 over 2. So you have plus V3 minus V4 all over 2. And everything here is equal to 0. So that's a statement of Kirchhoff's current law. And we know the value of V3 already. So I would be equal to, I plus V3. What's the value of our V3? Our V3 is equal to, from here, 6.4 divided by 4 plus, what's the value of our V3 again? 6.4 minus V4 is equal to, from here, we have our V4 to be 30. 30 divided by 2. Everything equals 0. So if you make I subject formula, that would give you let me still keep this on. 6.4 divided by 4, I have 1.6, plus if you do 6.4 minus 30 divided by 2, you'd get you get minus 11.8, right? And everything equal to 0. If you do 6.4 minus 30 divided by this, you get minus this. So I becomes, take this to the other side, 11.8 minus 1.6, and then I is equal to 10.2 milliamps, right? So this is the current due to the current I flowing after nodal analysis. So this is the solution to this question. You can as well find this value of the current by considering this current and this other two, and then this very one at this ground node. So that's another way. If you do that, I guarantee you are still going to get this same value, 10.2 milliamps. So thank you for watching. I'll see you in the next video. Like, comment, share, and follow my channel. Subscribe to my channel subscribe to my channel on YouTube, and I will see you in other similar videos. Thank you.